So now let's look at error tracing. That's the most important quality of ModelExplorer. It is accessed through the neighbor view menu entry, and you need to select error tracer. For this to work, your model has to be up to date. Your error finding has to be up to date with the model. We recently edited our model by adding an extra reaction here, so it's not up to date anymore. In order to make the model up to date, you need to go to Edit, Recalc, All or Recalc FBA. It's actually enough. Here, now you have recalculated the consistency, and now your error tracer mode should begin to work. As we see, orange crosses have started appearing, so it works. And also, let's delete this reaction that we just created to return back to original model. Now, let's do some error tracing and look at some examples fixing actual errors. So let's find some. Let's do a recalc here, and let's find some errors that we can fix. So here we have a somewhat long name. Well, it's a reaction that doesn't work, and you see these crosses. These are error sources, error source species for this reaction. If you hover over them, you see that this species is blocked in reverse. It's an irreversibility error, and this one is a source error. It's a source error because it's a dead end species. Nothing is consuming it seems. And this is a reversibility error because there are more than one reaction acting on that species, and all of them seem to consume it as well. So how to fix this dead reaction? We need to address that species and that species. So as you see, this species is produced, but it's not consumed. So let's add some reaction, call it R1, that consumes it. What is the species called? It's called 1392, and it should be a reactant. 1392 there, and shouldn't be any product, so it's just a sink. And we save that reaction. Now there is this other species, which is called 1373, so, and it is consumed but not produced. So let's add another reaction, call it R2 for simplicity, and it should produce this species, which is again 1373. There. And save reaction. Click cancel to exit the menu. Now, we were originally interested in this reaction, whether it be dead or alive. Now we will test whether our additions did anything to fix it. Let's do the recalc FBA, and voila, the reaction is now properly functioning. So these were reversibility and a source error. Another common type of error is called cycle error. So let's now start talking about cycle errors. These are errors which occur when we get cycles of reactions that shuffle around metabolites, and when it is not possible to remove or add any more of those metabolites. And in some models they're quite frequent. So let's find some here. Go to the error tracer node and let's find some reaction. Yes, let's recalculate FBA first. So there. Okay, we have FAD synthetase with a lot of crosses at random points in the model. Let's see what we find. Oh, okay. So here you see this blue region. This is a cycle. All species inside this cycle can be added or removed, while this black block here, which is a blocked module, a part of which our reaction is, this block module is interfacing this cycle and is caused by this cycle. It is caused by the fact that it tries to consume or net produce species within the cycle. So, how to fix this kind of cycles? So, onto the fixing. Here we have FAD synthetase. And we have a set of crosses which are the interfacing species between the blocked module and the cycle, and we want to find out how to fix it. So let's first take a quick look at the FAD synthetase itself. It's egocentric. So what does it do? Well, it seems to work by taking up FMN and producing FAD and using some ATP and producing some diphosphate in the meantime. So probably within the cycle we should be talking about cycles of FMN or ATP. So let's look back at what we see at the crosses, and indeed what we see, we have AMP, ATP and ADP inside the mitochondrion, which are blocked by the cycle. Similarly, we have FADH2 and FAD also inside the mitochondrion, and here we have riboflavin, FMN, which is related to FAD, and we have NAD. Similarly, here we have coenzyme A and NAD+. Now, when attempting to fix this kind of issues, one should probably first look at species which are related to the reaction one is trying to address. So FAD works on FMN as a reactant, which is here. So let's look at where we get it from by using the node ancestry. Well, apparently it's a part of a bigger cycle. By hitting tab we can check where it is going, and it is going nowhere as well. So it's stuck there in the mitochondrion, it seems. Okay, so first, in order to get this reaction to work, we need to get FMN from somewhere. FMN is now, as we see here, one way of producing FMN is through riboflavin, which is used by riboflavin kinase to make FMN from riboflavin. So, but what's the problem with riboflavin? I mean, why is it shown here? So let's show it. There it is, and let's see at its ancestry by using node ancestry. And okay, so riboflavin can be produced. Hitting tab, however, it cannot be secreted and is not consumed by anything that makes sense. Now, going back to our original FAD synthetase and looking at it in the arrow tracer mode, we see that a riboflavin is a part of a very small cycle consisting of FMN and riboflavin. So in case we cannot produce FMN or riboflavin, we should probably correct the import of riboflavin at least. So let's go here and see what the problem is. Neighbor view, node ancestry. There we have it. So what's the problem? Why can't it be exported back again? And here we see a reaction called transport of riboflavin. In fact, if we go and look at that reaction in ecocentric mode, we see that it's unidirectional. So in other words, that's why riboflavin can be imported and cannot be exported. So we can go to mode none and make it reversible to free up that cycle a little bit. So save reaction, edit, recalc all. Good, click cancel. Good. So let's go back to our FAD synthase and see. Okay, it's still blocked, but when riboflavin is still there, it's still a cycle. Actually, the reason is that we still cannot really consume it. Yes, we see here the FMN riboflavin cycle. So we must fix some other stuff, probably. And one thing to fix may be the FAD and FADH. So let's look at them first. Ecocentric mode. As we see, the ends of those lines align, which means that basically every reaction that tries to shuttle them in or out of the mitochondrion exchanges them for one for another. So we cannot get net more of them in the mitochondrion. In fact, if we look at node ancestry, it means if we can produce them or not. They are both unproducible, and the same applies to FMN. So we cannot get any more of them in the mitochondrion, so no reaction can consume them. Therefore, we should probably add some kind of shuttle of FAD between the cytoplasm and the mitochondrion. We can do it by adding a reaction. We call it R-FAD shuttle. It should be reversible and it should have FAD cytoplasm as one of its and the reactant, and FAD mitochondrion as the product. So we save the reaction, we do the recalc all. Okay, something changed. Let's see what did. Okay, suddenly we see FMN lighted up in green. That was quite unusual, so let's look at how the ancestry of it changed. So apparently nothing changed here, but the FAD can now be imported. Similarly, the FADH2 can be imported. So that's a decent change. And if we look back here, we see that it's done through riboflavin that we addressed before. So that's pretty great. But that's not all, because FAD synthase is still blocked. So let's go to error tracer mode and see what the problems still are. So we have addressed the FADH and the riboflavin downstairs there. It has even disappeared from the list now. But we still have the ATP AMP problem. So let's look at them with the egocentric view. Here we have AMP and ATP, and again we see that they are all being exchanged by the transporters. So again we can get more of them inside the mitochondrion. Let's look at node ancestry. Yes, we see this apparently that they can neither be secreted nor taken up. Okay, so we need a new shuttle for ATP this time. So we add another reaction, which we call our ATP shuttle. We make it reversible. We add ATP mitochondrion as one of the reactions, and ATP cytoplasmic ATP there as the product. And we save the reaction, and we recalculate everything. And now we see that there are even more green points here. Let's look at ATP and ADP using the node ancestry. ATP can now be shuttled in and can leave the mitochondria, and similarly does AMP diphosphate as well. So now going back to our FAD synthase, we see that it can take up what it needs, but it cannot secrete it. And the problem is that it secretes through FAD. Now let's go to FAD. Again, it can be taken up, but it can be secreted. And what is the reason? I mean, we added a bidirectional transporter here, which should be able to shuttle it out of the mitochondrion. So that's not a problem. Here we have the FAD from that we added. But now here we see a red reaction called FAD synthase. If we look at that one and go to egocentric, we see that it produces FAD in a one-directional manner. So in fact, whatever we pump into the FAD from the mitochondrion here cannot be taken up by any other reaction. And the reason is that the FAD synthase is unidirectional. So let's change it to bidirectional. We do that by going neighborhood none. Here we have FAD synthase, and we make it reversible. This, and we do a recalculate VA, and voila! Here we see our FAD synthase go very much alive. So, what does this mean? This means that with error tracer, it is relatively easy to find the sources of the errors that one could possibly encounter in a model and to fix them. Here we had a very difficult error, in fact, and by just changing or adding 4 reactions in total, we could fix it. So let's try the node ancestry because it looks so beautifully. So here we have FAD synthase, and that is uptake. Now let's see what happens to the secretion. Yay, it works. So thank you very much. This was another introduction video to the Model Explorer.